more difficult things to do algebraically. There's not a simple way, but we'll learn later that if the function has an inverse, then you find the inverse, and then the domain of its inverse is actually the range of the original function. So there's a way to do it. It's just there's not like cookie cutter do this every single time. All right, so now H. How many times does F intersect y equals -1/2? So you look at the y value of -1/2, which is right here, right? Imagine a line going like this. How many times does your function hit that line? 3 times. It's not asking where, right? It just says how many times. So the answer would be 3. Last one. When is f of x equal to 2? This is the same question, isn't it? It's saying when, it's not asking how many times, but it's asking when does this happen? When is your function's value 2? So look on the y-axis. Here and here, right? But here that was an open circle, so I don't count that. So I know it happens twice, but when it says when is this happening, they mean what x value makes it happen. So when x is equal to 4, or what was it over there? -5? Was it 4? Okay, I trust you. -4. So I could write it this way, since it's 2 numbers. Doesn't matter their order, okay? When you're doing these set notations like this and it's not an interval, it doesn't matter what order you put those in. It's just 2 numbers. So when x is one of these numbers, you get 2 out, right? Okay. That good? You all right with that? Good. All right, does someone mind erasing that? Can someone erase that for me, please? If you can reach. Can you reach that up there? All right. Now, I will mention something. Thank you. I will mention something else while I've got the camera on that. Everything that we just went over is stuff that an algebra student would be expected to determine, right? Just look at a graph and be able to tell, you know, where it's positive and negative and all that stuff. In a calculus class, what we'll ask is where's the function increasing or decreasing? So imagine you're reading this function like a book from left to right. Then decreasing would mean where the function's going down, and increasing would mean where it's going up. Right? And that's a more difficult question to answer in general. Like if someone gives you a function, it's hard to determine that. So in calculus, that's what you'll study. But you have to understand the positive, negative stuff first before you can start talking about when the function goes up and down. All right, back to the good stuff. Let me see if I've got more to show you here. Where is it? There it is. Who brought food? I hear food. Oh, that watermelon thing was pretty good. I liked it. Yeah, it's good. Yeah. All right, so let's look at the next section, because that's it for that section. It's just identifying things on graphs, really. So the next one, 3. Yeah, this one's long. Properties of graphs. All right, so we now look at a few properties of functions, which will become very important to us in calculus. First of all, what it means for a function to be called even. I remember talking to you about this before. I said, you know, if you plug a negative value into a function, does it actually change the function? And the example I think I gave you was something like this. If f of x equals x squared, what happens if I plug negative x into this function? It's negative x squared, but when you square a negative, what happens? It's still positive, so that's just x squared. So it doesn't matter if I plug in x or negative x, you get the same answer, don't you? That means that f of x is equal to f of negative x. And that's what we call an even function. Look at the power, it's even, right? That kind of has something to do with it. But it doesn't have to be an even power for it to be an even function. There's another function, cosine function in pre-cal that you'll learn about is also an even function. So that's the property of what it means to be even. Doesn't matter if you plug in positive 2 or negative 2, the function spits out the same thing. Now think about what that has to look like then. What is it going to look like if it's an even function? I said if I plug in 2, I get something, right? If I plug in negative 2, I should also get what? The same thing, right? If I plug in 1, I should get, I don't know, something. And then if I plug in negative 1, I should get the same thing. So if I do all this for all the different values, then what should this thing look like? Well, this one, symmetric, that's what I'm looking for. It should be symmetric to the y-axis, right? Like whatever happens over here, if this one does this and does crazy shit like that, this one's going to do the exact crazy shit over there that this one did, right? It's going to be a mirror image of it. Exactly, should. That's what an even function does. So here's an example of an even function right here. And here I have it where you can see if I move out x value, positive x or negative x, notice that the y values are always the same. See that? So it's going to look the same no matter which way you move. Yeah? Okay. That's called an even function. So even functions are reflections over the y-axis. Oh, I forgot I did this. So check this out. There's an even function, right? That's an even function. And this was to show you that it's a reflection over the y-axis. So I put it in three-dimensional space. See it? There's that flat sheet of paper. And now if you mirror it over, if you rotate it around, it's the same function, right? Mirror image of itself. Does it work if I go about the x-axis? Where is it? Oh, hold on. I think I have to move it first. No, that's for the next example, sorry. All right, now what does it mean to be an odd function? An odd function, what do you think a good candidate to give you an example would be? X cubed, yeah, x cubed actually works. And so let's see what happens with x cubed. And then we'll take a look at the picture after we try and figure out what it looks like here. So if I do x cubed here, what would happen if I plug in negative into this? It's still negative, right? But it's now x cubed. Right? So it's still going to maintain the negative. So are these two the same? No, they are not the same. Are they? Right? They're not exactly. So it's not even for sure. But what if I take my original function, I just throw a negative in front of it? Wouldn't that be the same as putting a negative in front of the x cubed? So even though f of x is not equal to f of negative x, negative f of x is equal to negative f of negative x. I know it's weird notation, but plugging in a negative value does not give you the same thing as plugging in the positive value, but it gives you the negative of that. Okay. Let's try and draw a picture. Let's say I plug into a function the value 2, and let's say it spits out the value 1, right? So this is f of x. If this is an odd function, what's f of negative 2? Well, it can't be 1, can it? Because then they would be the same. I said it's 1, but change the sign. So it would be -1. So it would be down here, wouldn't it? If I plug in, let's say, 1 into this function, it spits out 1/2. Then what's it going to be over here for -1/2? Or sorry, for -1. -1/2, so it'll be down here. Now I need to do something so you don't think that this is a line. How about if I plug in 3 and I get this right here?
Or you get that right there.
At -3, I would get this distance, right? But positive, so it'd be up here. Yeah? Okay, so let me draw this. Anybody want to come up here and try and draw the other part of this? If this is an odd function? You went, does that mean you want to do it? No? You want to try it? All right, go ahead. No? No? Okay, you tell me. You tell me. I'll close my eyes. You just tell me what to do. No, you got it.
Right? It's that right?
I don't know. I don't know what you want to do. Sure, that looks right. What do y'all think? That's good.
Okay.
What do y'all think? Okay, so for an even function, even, the one we did before, it was simply just reflected over the x-axis, wasn't it? Is this the same thing? Is it not the same thing, but is it a simple reflection? Like if I take this black part to get the red part, is it just a simple reflection? What is it though? I mean, can you tell what it is? It's a reflection over the x first and then over the y. Or you could say it's a reflection over the y and then over the x. It's a double reflection. Make sense? That's what all odd functions look like. So I have a little bit of an animation here. Everyone agree that's an odd function? Yes. Right? So for every x value, I go out to the right, it goes up green, and then on the left side, it goes out and it's below the x-axis instead, right? Same length. And then when I get over here, now my green one is negative, now my yellow one has to be positive. Yeah? Okay, so it's double reflection. There's an odd function. Whoa, why is it so big?
So is that basically inverse?
What do you mean?
Just the way that it's set up, like just inverse? Like how you have a fraction of 1 over 2, then 2 over 1, is that kind of, that is, or?
Well, it doesn't reciprocate.
Okay. That's
Yeah, because I don't know if this is what you're saying, but like when you plug in 2, if you plug in something you get 2, then on the other one would be 1/2. Is that what you're saying? Or no?
Well, like, yeah, kind of, well, like I said, like with the fraction 1 over 2, 2 over 1 there, and that's how you inverse it. I was just wondering if it was that way with this, but with the points. So the way that it's set up, it's kind of like going the opposite.
I don't know if I want to use the word inverse, only because we really reserve that word for truly what an inverse function is.
Okay.
Or an inverse operation, which would be the opposite operation. This is, you know, to get a picture of an odd function, you can take one part of it and you can reflect it twice, and you would get the other part.
Okay.
So look at this one right here. We're going to look at it in three-dimensional space again, so you can see it. So if I take a reflection about the y-axis first, okay, that is not correct, right? But now if I take that and I rotate that around the x-axis, it lines up right on top. Make sense? Okay. That's what odd functions do. So does a function, if I give you a function, just write some function up here, does it have to be even or odd? Is it one or the other? No. You can have functions that are neither or neither odd nor even. So there are three possible things. You either have even functions, odd functions, or neither. I'll give you an example of neither. There, that's neither one. That's neither even nor odd. We won't graph it, but it's just not. Okay? All right. So do you understand how you would well, you know what? Let's look at this one because I think it's worth it. Is this function even or odd? I told you it's neither. But how would you check it? Well, first thing you would do is you would say, what's f of x? I mean, sorry, what's f of negative x? So plug in negative x. What would you get? Negative x cubed would still be negative x cubed, right? Would it matter here if I plugged a negative in here? No, so that would be still this? Are these two the same? So it's not even, right? These would have to be the same for it to be even. So now what we do is, since we can say it's not even, let's look at this and let's compare it to this one with the negative in front of it. So change the sign of the original function. Wouldn't that be negative x cubed minus x squared? Are these two the same? No. So if these two aren't the same and these two aren't the same, you've checked even and odd right there. It's neither. All right? Neither. So how do you spell neither? And what? N-E-I. Well, I know the rest. I'm bringing this up for a point, to make a point that I don't like the English language. Because I learned the I before E thing. Right? I before E, except after C.
And something with neighbor.
And who knows this rule? The correct version of this rule. Anyone here? Good English person here? What is it? I before E? You what? You just know it? Is that what you said?
I'm an American.
Why is this not IE? Because I thought it was I before E except after C, except when it's overcast outside and it's Thursday, right? I mean, this is why I chose math instead of something like this, because you can't have a rule that only applies sometimes, right? In math, the rules apply all the time, pretty much. I mean, like, there's no variations. Like, you know what? Today we're going to, multiplication is going to be something different today than it was yesterday. Or, when you have this, then you do it a certain way. So I gave up a long time ago with the IE thing, and I figure it's a 50-50 coin flip every time I write something with I and E in it.
Maybe it depends if you draw to neither.
Yeah.
How often are you writing with your hand and stuff like that?
Well, even when I type, I've got the spell checker, so that saved my butt big time.
You won't even know you did it wrong.
Okay, so let's look at another. We have 20 minutes. Let's look at this definition. We have new definitions. What I was talking about, increasing and decreasing. All right, this is different than anything else we've been talking about so far. The definition of increasing and decreasing is somewhat complicated. So I'm going to write it down on the board first. I mean, it's up there, but I'm going to draw it for you and see if it makes sense to you. Let's say that I have a function that is going up as you read it from left to right. That's all I'm going to tell you, that when you're drawing it, it has to go up. So would you agree that this is going up? Yes? Yes. Okay, now let's try and establish a property that would explain to someone who doesn't see the picture that it's going up. So here's what I'm going to say. If I pick a value, I call it x1. I used x1, right? And I pick something to the right of it, x2. Yes? So if x1 is less than x2, that just means that you have 2 points, one of them is to the left of the other one. Yes? Then in order for this to be going up, doesn't this height have to be smaller than this height? That height has to be smaller than this if it's going to go up. Then f of x1, that's the function's value, that's the height of this function, yes? The height of this function at that point must be smaller than f of x2. Yeah? That's what the definition says. That's what it says when it's this first part. This is the definition the way a mathematician would write it. A function is said to be increasing on the interval I. So there's some interval here that I'm talking about. Some interval here, I. That as long as you have a point to the left of some other point, okay, so x1 is to the left of x2, then the height at x1 is smaller than the height at x2. Well, that's the way we write it as math people. It's very precise and to the point. It's going up, yeah, I know. Believe it or not, the precise definitions are what we use to prove theorems, difficult theorems. We have to have precise ways of writing things. Okay. Now, what does it mean if the function's decreasing? The only thing that changes, right, is that you're coming this way. This is still the same, right? You have a point to the, to the left of another point. All that switches is this. So this changes like that, and then now you're decreasing. Now we're counting on reading this thing from left to right, like a book, right? Don't Chinese that read from right to left? In China, right? Chinese books, right to left? I think so. But we're counting, we're kind of going off of, we go from left to right, so that's why this inequality looked like this. All right, so that's the second one. How about f is said to be constant? Well, what would it mean for a function to be constant? It means it's flat line, right? Just like that. Well, that would mean that if I take 2 points again, right? If these two were different points, then the heights of them would have to be equal. And as long as that's true on some interval, then it's constant there. It's flatlined. Make sense? Visually, does it make sense with the definition now? Because if you just read that for what it is, it can be like, what? All right, so that function's increasing, right? I have some other animations here. I actually connect the 2 points with the dot with an arrow, and you can see increasing is going up, right? And then decreasing is going down. And constant's flat. So we don't need those. What's that? All right. All right, I'm going to go up to the board. Boy, that's going to be kind of hard to see that. All right, let's take a look at this. Y'all doing all right? We still got another 15 minutes. Y'all gonna make it? Come on, you can do it. Yeah, I know. Yeah, I really don't think that's coming out on the video at all. All right, so there we go. I wonder if I can change this exposure. All right. I doubt that's coming out on the video, but we'll see when I actually put it on YouTube. There's like a real bad glare coming off of it. Okay, so this function here, this arrow goes down like this, and up there goes that. Okay? So that's our function. Where is it positive? Where is it negative? Right? Where does it hit the x-axis? Those are all things we could have asked. That's not what I'm asking now, though. I want to know where it's increasing. So where is f? Where is f increasing? I like to just do that. Go ahead.
From negative infinity to negative 1, and then...
Okay, stop right there. So you're looking at x values, right? And you're saying that, imagining that this goes down and forever. So if I'm coming in this way, I'm coming up. And that's as far back as I go. So negative infinity all the way until I get to that top right there, which happens at an x value of negative 1. Yep. So everywhere here, if we're reading this from left to right, we're coming up, 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 up. So from negative infinity to negative 1. Do I bracket this, or it's kind of... With increasing and decreasing, always use intervals. Always use open intervals, meaning don't use brackets. With increasing, decreasing. Just that's the rule of thumb. And the reason is because you can't even talk about increasing at a single point. Right? If I just give you a point, can you tell me if that's increasing or decreasing? No, you have to have a second point to compare it to. So having that endpoint doesn't really matter. Okay, but you said that's not the only place.
Yes.
So where else does it increase?
From 1 to...
So here, I'm assuming you're thinking you're going down, and then you get to here, and now you start turning back up. Yep. So that happens at 1, so union 1 to infinity. That's where the function's going up. Any questions on that? Where's the function going down? Just in that one little window right here, right? Between -1 and 1. Yeah, if you mean if you did a reflection or, yeah, did something, yeah. That would all switch it, but. Okay, make sense? All right. See what else is here.
I have a question.
Yes.
Error one. Oh, George, oh, never mind, just kidding.
Okay.
George, read.
All right. This is actually this is actually a slide that I made for my calculus class, but it's something that we could look at in here. This one, it's probably a little bit harder to tell where things are happening. Don't worry about that. But there are some things happening on this function that are somewhat interesting. So ignore what this is saying right here. This f with this little mark on it, just ignore that. What I'm going to do is just move this line along. What I want you to notice, remember we were talking about the difference quotient and how it gives you the slope of that line? Notice that I'm increasing over here, aren't I? Let me take that back out of there. That part that you would say is increasing is all of this, yes? And if I put a tangent line anywhere on that graph, notice that the slope of that line is positive. When I get to the top, come on, do it. Well, there. When I get to the top, right, I'm at the highest part of the function. Now, not the whole function, because it goes off to the right, up forever. But do you agree that over here, I'm the king of the mountain right here, right? There's a higher point over here, but over here locally I'm the maximum. Do you see that that maximum is taking place where we went from increasing, where we changed from increasing to decreasing, increasing to decreasing? That a maximum occurred there? Yeah? Now look over here. I'm decreasing, right? Decreasing. What happens when I get to this right here, right in there? What happens there? I'm still decreasing. Even though I flattened out, I'm still decreasing. Decreasing, decreasing until I get here, and then I will start to increase again. And notice that at that bottom point, I went from decreasing to increasing, didn't I? So it looks like maybe if you ever in calculus want to try and find the highest point and lowest points on graphs, it might be in some way connected to the relationship between where your graph goes up and down. And that's exactly what you'll be doing later on. So definition of an absolute maximum and minimum values. Given a curve f defined on some domain and some number c, then f of c is called the absolute maximum of f on d if f of c is greater than or equal to f of x for all x in d. What? What does this mean? What does that mean? Okay, let's say that we have a value. That's not a good function. I need to give you another one to look at. Here we go. Look at this function right here. Is there a highest point on this curve? Yes? Where is it? Right around here? Right there, right? That's the highest point on that curve. And it is called the global maximum. It is the highest point. It's some value, it looks like at 2. At 2, it is the biggest, it's bigger than every other function value. Yes? Does this one have a global minimum? Yes, down here. Now the key to it though is that I put these ends on the function, right? If I didn't put those ends on it, you couldn't say this. You could say global min, but you couldn't say global max. So like this one. Oh yeah, also absolute max global max, same thing. So when you see absolute maximum or global maximum, they mean exactly the same thing. So this one, yeah, this one it would not have a global or absolute max or min, would it? This is not the lowest value because there's one over here and it keeps going down. This one also doesn't have an absolute maximum. All right, now what about local maximums and local minimums? Local maximums and minimums have to do with whether or not you're the king of the hill or bottom of the valley in your little neighborhood. So look at this value right here. Is it the lowest value on the entire function? No, but is it the lowest value in this little area? Yes, that would be called a local minimum. This would be a local maximum. But it's also the global maximum, isn't it? So you can be both the local and global at the same time. And global and local minimum at the same time. All right. Where's the global maximum happening? Where's the global maximum? Up there? On the board right there? In red? Okay, thank you. Where is it? At 10, x value 10, up here. That's the global maximum. How about a global minimum? Right around here? How about local minimum? Is this a local minimum?
Yes.
That's a local minimum also, isn't it? We have two of them. How about local maximums? Here, right? So we can look at these. Here are the local ones, right? Locally, these are either the lowest or the highest. And then globally, we only have these two. All right? Does this one have a global maximum? No, if we assume that these are arrows going up forever, no global maximum. Do we have a global minimum? Yes. There it is. And then all of our locals, how many locals will we have? 3. 1, 2, and then 3. Global. Do you have a global maximum? Yes. What's different about this global maximum? There's 2 of them. I mean, in other words, it happens at 2 different places. It's the same y value, but it happens at 2 different x values. How about global minimum? Same thing, 2. How about locals? 3. 1, 2, 3. And then your globals are those 4. This makes sense? There's not, I mean, it's just more of a visual thing right here. All right, the extreme value theorem. If f is a continuous function on a closed interval, then f attains both its absolute maximum and minimum on the interval. So I'm going to show you a picture of this first. What do you think it means for a function to be continuous? Kind of. If you draw it, you can draw it without picking up your pencil. That's basically what it means to be continuous. So this theorem is saying that if I draw a function on a closed interval and I am not allowed to pick up my pencil, then I have to achieve an absolute maximum and an absolute minimum. There's no way around it. So look at these 2 points. You see these? I am going to connect those 2 points with a curve. Here we go. I shouldn't have showed that. There we go. There's my curve, all right? Do I have an absolute maximum and an absolute minimum? Yeah. Yes, there they are, right? So let me try a different one. Let me draw this one. All right? Do I achieve an absolute maximum and minimum? Yes. The extreme value theorem says there's no way for me to do this without achieving a maximum and minimum, absolute. How about here? The two endpoints, right? What about this one? Does this one have an absolute max and min? No, but is it continuous? No. I cannot draw this without picking up my pencil. See, I would go like this. This dotted line means that this goes up forever right there. There's a break in the graph. So because I can't draw it without picking up my pencil, it's not continuous and the theorem is thrown out the window. Boy, this is a problem. I think this is a good take-home quiz. What, man? You suck, man. So look at this. You've got this function right here, right? And I ask you the intercepts. What do I mean the intercepts? Where does it hit the x-axis? Where does it hit the y-axis? The domain and range. Fine. We already talked about that. Where is it increasing and decreasing and constant? I gave you an example of increasing and decreasing a minute ago. Constant would just mean it's flatlined. And then find the local maximums and minimums, global maximums and minimums. And when I say find these local maximums and minimums, just list them as points. Like I'll give you a hint. This point right here, -1, -2, -3, -4, -5, -6, +2. The point -6, +2 is a local maximum. But you got to identify all of them. All right, that's going to be a quiz. It'll take place, be due when we return, which may or may not be Monday, right? I told you, still don't know. All right, I believe that's all we can do right now, but I want to show you something. Just give me 2 minutes. Y'all can pack up. The other one? Yeah. Anytime I give you all an assignment and ask you to turn in, y'all should just, it should be the first thing you do when you come in. Just throw it on my desk. Yeah.
Yeah, see, I did both of the things. With all the homework, it was doing those ones.
Anyone else that wants to turn in the quiz, they can. What? What quiz?
This is a D&E, right? Is that what it is?
Yes.
Okay.
Uh-huh. Thank you. All right, so here's the problem I wanted to show you. Oh, come on. Let's get this thing. So for my last 60 seconds that I have here, let's say that I have a wire, all right? Now, this problem is not going to seem like it's very applicable, but let's say I have a wire, and I'm going to cut it somewhere. And for the first part of it, I'm going to create a triangle out of this wire. Little triangle, okay? And then the other part, I'm going to take it and I'm going to form a circle. How do I do it so that I get the most area out of both the triangle and the circle? Well, what winds up happening, and this is what calculus is going to be about, is that you wind up getting a function that you graph. Here it is right here. This tells you the x value is where you cut the wire, and the y value is the actual area. So if I want to know where I would get the most area, I would be trying to find the highest point on that graph, which turns out to be use the whole wire as a circle, and you get the most area possible. But if I want to find the least area, then I need to find the lowest point on this graph, which corresponds to a local minimum. So even though in this class we're like, what? We're finding top and bottom function, like, who cares? Later on we tie it to like a real world problem, even though the wire doesn't make a whole lot of sense. And it works out for us to mean something. Here's another one. You're filling up a cone, right? You're filling up this cone-shaped thing, and you're trying to find a function that somehow gives you a relationship here. And so look, again, I'm looking at a function. The whole thing is these functions mean something later. They're tied to something. So we need to be able to work with them, be comfortable with them. Domains, ranges, maximums, minimums, increasing, decreasing, all that stuff has to be in our toolbox. All right, y'all have a good weekend, right? Because it's Wednesday already. Check your email when? Saturday. I think I said 8 p.m. By 8 p.m. Saturday, I will tell you whether or not we're doing Monday. I didn't take it. Yeah, I forgot. So you're good.